Hello, this is going to be a brief demonstration of measuring RS-232 signals and asynchronous data using the Picoscope. The very first thing you want to do is to set up the channels, the trigger, and the time base of the oscilloscope. So I'm going to come over to channel A, which happens to be the blue channel, and I'm going to select probes standard times 10. That's important because you should already have the physical probe set so that the switch is moved over to the times 10 position. The other thing you want to confirm is the setting for the voltage on the scope. So the maximum voltage and the minimum voltage you'll see on the screen. I have mine set to plus and minus 10. So you can see at the top, it's plus 10 volts. Down at the bottom, minus 10 volts. It's also important to choose the correct time base. In my setup, I'm going to be measuring bit times that are about 104 microseconds wide. So 1 millisecond per division would be an appropriate time. And what that means is that from this division here to this next division is 1 millisecond worth of time. You can go up or down from that by connecting on the blue plus and minus. Okay, so that may change as we make some different measurements, but for now, 1 millisecond is a good setting. The next thing we'd want to do is to look at triggering, and for now, I'm going to set it to none, because this is a good setting whenever you want to check whether or not you have a signal. Okay, you can see this signal is not triggered. Obviously, it's shifting left and right. But I know right away that I do have some signal that's being transmitted from the Arduino. So this is a good test to see that you are getting something. Once you are receiving a signal, the next setting you'd want to choose is auto mode. So I'm going to come up here and select auto. And that does make things a little bit better, but it's not perfect. And that's what we have to improve. So this is auto trigger. I've got 0 volts set in the center, and notice I can move that up and down, but for now I want it in the center. And we have to look at things like trigger level and trigger type. So I'm going to change the trigger type to, and you do that by clicking on this, I'm going to change it to pulse width. And you want to select channel A. Pre-trigger is 10%. That just means it's going to trigger on this 10% point. This is 10, 20, 30, and so on. I'm going to leave the delay at 0, and the threshold is very important. You may want to move it up and down, and this yellow diamond is actually the threshold. The hysteresis, you'll notice that this little yellow line going upwards is changing the hysteresis value. So probably 2 or 3% is a good number to work with. We want to use positive pulse detection. And what this means is it's going to wait a period of time after the pulse is high for a certain amount of time. And I do want to set that time to being greater than maybe about 2 milliseconds, because in my program, I do have a 2 millisecond delay. In this next section, we want to look at the Arduino program. It has a couple of comments, then it goes into the setup program, and really there's only one line, which is serial.begin and then 9600 serial underscore 8 and 1. And what this is identifying is that we're using the first serial port, the transmit and receive data. We're going to transmit at 9600 bits per second. That would be about 104 microseconds per bit. It's 1 over the bit time that determines the length of one bit. And the 8 indicates we're transferring 8 data bits. N for no parity, and 1 for one stop bit. Once we've set that up, we're going to go down to the looping part of the program, and we're going to perform a serial write, and we're going to write the letter A. And the ASCII code for the letter A is 41, which is a hexadecimal code, and then a 20 millisecond delay. Back to the Picoscope to set up our triggers and a method of capturing the serial data and decoding the serial data. So the first thing you want to do is make sure that you do have a stable signal, and we do here. So it's auto triggered. We'll change the type to pulse width. The pre-trigger at 10%, the threshold, that's this yellow indicator, 2 volts. We want to have a positive pulse before the trigger occurs, and that pulse should have a length of time which is greater than 2 milliseconds. So we do have all that set up. The next is to go to serial decoding. So click on this icon, RS-232 UART, and then click next. And here we do want to trigger on channel A, that's important. We don't want to invert. We want our threshold to be about 2.5 volts, so that's fine. And we're operating at a baud rate of 9600 bits per second, or 9.6 kilobits per second. We're using 8 data bits, no parity, and 1 stop bit. And the data is being transmitted serially with the least significant bit being the first bit transmitted. Once all of that's set up, click next. Here we're just telling the system that we want to display our information in, we'll start off maybe in binary. And we're going to have a table down the bottom, and the table is going to be in hexadecimal. And then the rest, just leave it as it is. And what you get, and you can shift this up and down, is a pattern of 1s and 0s representing the data. And I can scroll this table up, and you can see that we're transmitting the character 41. And it's least significant bit first. So this is 0, 1. This is where the 4 is coming from, and the 1 at the very final bit position. Now I'm going to zoom in a little bit, and I'm going to re-trigger this. But I'm going to zoom in, and I do that by changing the time base. I'm going to, I think that's going to be a good value of 200 microseconds per division, because our data is 104 microseconds wide. So that seems to be appropriate. The next thing I'm going to do is to measure each of the bit times. In this part of the video, we'll go through on setting up the bit time measurements, and we're going to do that with cursors. So the cursors normally sit here over on the left-hand side for channel A, and one at a time, I'm going to move them over and try to line it up with the time for one start bit. So the start bit begins on a falling edge, and it's a logic low at TTL levels, and then it will switch to data bit 0, and 1 over 9600 is going to give us 104 microseconds. So the predicted value and the measured value makes sense. The next measurement I will make is how long it actually takes to transmit that letter A, 1 character or 1 byte of information. And at 1 over 9600 bits per second, that's equal to 104 microseconds. And this information transmits 10 bits. So it's the start bit. This first bit is data 0, 1, 2, 3, 4, 5, 6, and data 7. And then after all the data is transmitted, we have the stop bit. The stop bit is always there. The start bit is always there. So I'm going to move this cursor all the way over to here. And if I multiply 104 microseconds times 10 bits, that gives me 1.04 milliseconds. And you can see that right here, I am measuring that difference in time between the two cursors. So what I expected, what I measured are working out. In this next step, we want to measure the RS-232 signals. So the first signal set that we measured was at TTL levels. So the logic low and logic high were typical TTL. If I bring this cursor down, you can see that the high voltage level in this case is about 4.8, and we have my 0 set here, so the low level is about 0 volts. Now, to be able to measure those signals, we have to turn on channel B, and we have to make it times 10, and we have to set our probes. So you do that by coming over to vertical, clicking on manual, and that turns it on. And we want to have it set to plus and minus 20. It's going to be a greater value than A because we're working with RS-232 levels. So the other thing we want to make sure is the scope probe is set for times 10. It is in this case. So, just review this area here, times 10, plus and minus 10 for TTL. plus and minus 20 for RS-232. The other thing we're going to do is maybe shift the signal up and down. So I'm going to close these probes. Okay. And I'm going to shift the TTL levels up a little bit. I'm going to get this cursor out of the way. And I'm going to come over here. This is a really important part that sometimes is tricky to get right. But you bring the cursor, the mouse, over to where the 0 is. And you can see there's a tiny line. And this allows you to shift it up. But what's important here is you want to shift it and have it lock on a 0. Okay, not at 0.2, not at minus 0.1, lock on 0. And you can shift this line, the decoding line, up a little bit. It does not have to line up on a line. And then we're actually going to shift the RS-232 signal. So for that, since it's on channel B, you come over to the right and you see that line there as well. And you get this cursor that allows you to shift it up. And I'm going to shift it until it locks in on a 0, and that works right there. Okay, that's 0. So when you do the demo, you want to make sure that the TTL levels, the bottom part, are at 0, and for RS-232, that's at 0 as well. Okay, so everything is set up to measure the signals. And you will notice that for RS-232, everything is the opposite. Okay, it idles at a low level, and it transmits the data at a high level. Now for the RS-232, you have to come over to the right-hand side. This is where you're going to set your cursors. So the cursor sits up here. Bring this down. So that's going to be the high-level cursor. Bring a second one down. And just put it in approximately the middle of that data. And as it indicates in RS-232 voltage levels, the center should be around ground, which it looks like it is. So there's my ground signal. And it goes to a positive voltage, somewhere typically between 5 and 12 volts for many interfaces. And for the low level, between maybe -3 to -12 volts. Okay, so it is at RS-232 levels. That's all I want to see. And maybe you can put a cursor here. We've already measured the bit time. We can do it again. Well, actually, we still have our cursor sitting here telling us the whole byte took 1.04 milliseconds. So this is kind of the capture you want to see for the RS-232 lab. It's showing the high level, which is called space, the low level, which is mark. The low level is also the idle level. And in our case, it's about -6 volts. The appearance is exactly the same as the TTL levels, but opposite. Okay, that's important to understand. And when no data is being transmitted, that's called the idle level, and it's at the mark voltage. You can remember that with the letter M being about -6 volts in this case. When data is actually being transmitted, it's at about 7 volts in this particular case. Okay, so the markers tell us that information. So 7.27 for the red B channel and minus about 6 volts for the B channel at the low level. Right, here we're back at the Arduino program, and the only thing I've changed here is instead of doing a serial write and the ASCII code for 41, which is a letter A, I'm going to print my name on the screen, and we're going to decode it to actually see it. Now, since I'm using a print line, it will also print something called a carriage return and a line feed. These terms come from the days of typewriters, where you had to move the carriage, the whole movement where the paper was attached to, over to the left and move up to the next line. So you would rotate the carriage. So that's called a carriage return and line feed. So that's the program we're going to work with. I want to make sure it downloads okay. So I'm downloading this. Now, this is kind of what I wanted to show you here, that seems to be stuck at uploading. Sorry, that's the term I should have been using. But there's a little switch on the board, and you want to make sure that that's off when you're downloading or uploading the program. Sorry. So I'm going to try it again. And you might get this error. Try it one more time. And it says uploading, done uploading. This is because of the switch on the board. So just be aware of that. Right, on this screen, what you're seeing is actually my name being transmitted serially at 9600 bits per second. And I'm looking at the information in binary, so that's maybe not a good way to do it. So let's actually change it to the code for my name, the letters. So to do that, you just come over to here where it says RS-232, go to next, because all those settings are fine. So we want to display it in ASCII code. The table down at the bottom can remain in hex, that's fine. So let's do finish. And now what you're seeing, so when it triggers on the start of that signal, the letter M, I, C, H, E, L, and then there is the carriage return and line feed. Now that data is required, so it takes up some of the time. And as I said, there's always a start bit, logic low. There's always a stop bit, a logic high. And there are 8 data bits that are being transmitted. So that's 10 bits in total for each character that we transmit. And we're transmitting 1, 2, 3, 4, 5, 6, 7, 8. So if you want to figure out the time for 8 bytes of information, it's 8 times 1 over 9600. And then the number of data bits, so that's times 10. And when you do the math on that, it gives you about 8.3 milliseconds. And you can see we have our cursors at the beginning of the start bit and at the end of the stop bit, and that's measuring the time that we expected. So it's working out correctly. And that's another part of the lab that you have to demo. Okay, so you want to make sure, I'm going to move this out of the way a little bit. I'm going to move these cursors out of the way. They're not needed anymore. And it's just showing me the time. And it's shown up here as well. So it shows where I started and where I ended at 8.33 milliseconds. And down here is the table showing the ASCII code for the letter A, and then the I, the C, and so on. In this example, we're going to actually change the time of the serial transmission. We're going to bump it up to twice the speed, to 19,200 bits per second, but we're still going to use 8, N, and 1. Now, since we changed the speed, we have to change values in our serial decoding, because as you can see right here, we're not getting what we expected, the letter A and the letter C. So what I have to do is come over to this little box where we've set up the serial decoding and click on, right here, this will do. I think if you bring this pull down window, you actually get a lot of choices. So we're going to select 19,200 bits per second and then just click next and finish. And now, great, it's displaying the value A and C. And we were only able to get that because we changed the serial decoding. Now, since it's only taking up a bit of the screen because of the different speed that we have, let's make this a little bit wider, but not too wide, because if you go too wide, it's off the page and it doesn't serial decode correctly. So it's still TTL levels, and what it's showing you is it's transmitting the letter A, which has a code of 41 and 43. So here's the start bit, the 8 data bits, the stop, and then the start, 8 data bits, and the stop for the second letter. And the whole length of time to transmit the data should be twice as fast. So it's 10 bits for the first character, 10 bits for the second character. So that's a total of 20 bits at 52 microseconds per bit. And that adds up to 1.04 milliseconds. Makes sense because the single character A took that same amount of time, but we're at twice the speed now. So we're able to get twice as many characters out at the same amount of time. In this example, I've actually made a change to the parameters I'm using for transmitting data. I've changed it back to 9600 bits per second, which is 104 microseconds per bit. And I've changed it to even parity. Okay, so I actually might want to change it to 7 data bits. So I'm going to do that. I'm going to pause this. So here's my Arduino program, but I'm actually going to make this 7 data bits instead. So let's make that change and we'll download this. So it's 7 data, even parity, 1 stop bit. We'll download it. Okay, now that we're done that, we can switch back to our other program. in the Picoscope. Here we go. But since I've made all these changes, I must go and change some of the parameters that I have in this software. So I'm going to go to the serial decoding. And here we've changed back to 9600 bits per second. So I've changed that. We have 7 data bits this time, and we have even parity. So I've changed all those. Click on next, leave that the same, and voila, everything seems to be working out okay. But there are some differences here. If we look at the information, we still have a start bit at a logic low. This is our D0, D1, D2, D3, and so on. This would be our D6. We're not actually transmitting 8 data, we're transmitting 7. But we're transmitting a parity bit to check for errors. Okay, and what the parity bit does is it looks at all the high data bits. In this case, we have 2 of them. And including the parity bit, we want to have an even number of high bits. So we already have an even number, so the parity bit is going to be 0. Now I'm going to change the time base slightly here to include our other data bit. And this is a C. And the C has a different number of highs. And what I can do to analyze that is actually go back up to serial decoding. This makes it a little bit easier to look at the information. And we're going to change our data to binary. Okay, and click finish. So this actually makes it a little bit easier to analyze. And in binary, remember we had the letter A and the letter C. Probably have to remember that because of the changes that we made here. And this is the least significant bit. This is the most significant bit. So that's a 41, and this is a 4C. And we have even parity. So notice that the parity bit, since we already have an even number of 1s from here to here, the parity bit's going to be a 0 to keep it even. But over here, we have 1, 2, 3 high data bits. So that's an odd number. So what the parity bit will do is change its value to a 1 automatically before it transmits, and the receiving side will verify that there are actually an even number of bits, including the parity bit. So that's even parity. So I'm going to actually go into the program and make a change to odd parity. So let's see what happens when I do that. So we're back into the Picoscope, and look what's happened down here. It's doing a parity check and it's giving me errors. I didn't expect that, but I have errors here. And the reason is that what I'm testing for and what I'm sending are not the same. So I have to match it up. So I'd come over to here and go to, in this case, we want odd parity now. Okay, it's still 7 data bits, still 9600 bits per second, but I changed the parity to odd. Notice that this is important to notice here, that it doesn't have a start bit anywhere. And that's because the start bit is always included. Okay, so now, look, there is a check mark down here. So the parity check is passing. The difference is, though, I've selected odd parity. So now, if I add up all of the 7 data bits and the parity bit together, I have an odd number. 1 plus 1 plus 1, that's equal to 3. That's an odd number. Over here, 1 plus 1 plus 1 plus the parity bit of 0, that's an odd number. So the parity bit actually changed to the opposite. For the first byte of data, it's a 1. For the second byte of data, it's a 0. So that kind of explains the parity bit for you. Hopefully all these demonstrations will help you do the lab. See you later with another demo. Bye for now.